Today we're doing a sample problem from chapter 5. This situation has us finding the acceleration of two blocks that are put next to each other. So it gives us a force applied to these two blocks and that force is 20 newtons. And the force is actually applied to block A, but then right next to that block is block B. And so those are going to slide along the frictionless horizontal surface and accelerate. So let me pause here and make a picture to go with this. So here we have, let's say this is block A and this is B. And when they talk about the applied force, that is coming and touching block A. But, of course, that 20 Newton force is going to affect the motion of B because they're going to move and accelerate together. Okay. So as we try to figure out the acceleration of the blocks, we have to decide, what we're going to draw free body diagrams of, okay? Because my advice was to always draw a free body diagram, okay? If we pick just block A, and we isolate block A and consider the forces on it, right? Then we would have the force applied, which we would draw as like a pull, because you're supposed to draw it out from the dot. But actually that wouldn't be the only force. There would also be the normal force of block B, like resisting against, that acceleration, okay, because if B wasn't there, right, A could just go flying. But the idea that there's like that pushback from B's inertia, that we don't know that force, and so that kind of stinks. So I feel like, we just are at a dead end because we don't know that force. So instead, the trick that we would use with this kind of problem is to actually expand our system bigger and make the system be the combination of the two blocks, like as if they were glued together, which they're not, but when you consider the two blocks together, then that force of block B on block A and the force of block A pushing on block B, those two become internal forces, that don't affect the acceleration of the system. They are literally internal, right, inside the green circle here. And so when I draw the free body diagram of that green system, then all I have on the free body diagram is the applied force, and then the FG and the tables supporting it, and these two forces, sorry, I shouldn't use those congruent symbols, but I don't have a grid right here. So then all the net force, okay, on the system would be equal to just the applied force, and I know that it's 20 newtons. That makes life so much easier. But then the mass of the system would have to be the combination of the two masses, which is going to be 4 plus 6, which is 10 kilograms. And then when I'm going to use Newton's second law to get acceleration because I know both of these quantities. So I can just do 20 over 10 and get 2 meters per second squared. Okay. And then it asks for one of the specific forces that we were just talking about. It asks for what is the force of block A on block B. So then if you're just now focusing Okay, let me erase some of my doodling here. Now we care of just about block B, right? And I'm going to draw a free body diagram of block B. So this was the combo, right? But now for block B alone, what are the forces on it? Well, it's not being touched by the applied force. So the only thing that is making it accelerate, right, is the force of, like, the normal force, basically, of the surface of A, pushing on it, or like A on B. And then I've still got, of course, the table or the floor, or whatever that is, and gravity, which can't go. There's no friction. So that's interesting, because then I'm sort of working backwards. I want to solve for the force of A on B. It just so happens that that is equal to the net force, because it is the only force that doesn't cancel. And so then I do know its acceleration. It is accelerating along with block A at 2 meters per second squared. They both accelerate together. And I know its mass. So I can use Newton's second law to find that force. So I'm just going to do, let's see, this is the 6 kilogram one. Now I am just using that one mass, just that block, okay, and multiplying it by the acceleration value and getting 12 newtons of force that it takes, okay, to accelerate. So does that make sense that A is putting a 12 Newton force on B in order to accelerate it like that? Okay, well, what, like, yes, because it's less than 20 newtons, okay, because in order for A to accelerate at 2 meters per second, it needs like 8 newtons of the 20 newtons, you know, it needs its fair share of that 20. So 8 of the 20 goes to accelerating A, 12 of the 20 goes to accelerating B, and that's how we get these total of 10 kilograms accelerating to the right.